The guest is with us now on the behalf of Civil Engineering Department. On the behalf of Civil Engineering Department, Tulsiramji Gaikwad Patil College of Engineering, Nagpur, I welcome Professor Suyog Dhote, Assistant Professor, Ramdeobaba College of Engineering, Nagpur, on the topic statically determinate and indeterminate structure by force and energy method under Prerna scheme sponsored by AICT. Sir, I request you to please take over the session now.
Okay, thank you. Okay, so very good afternoon to all of you. Is this visible to all of you? Is this visible?
Sir, your presentation is not visible.
Presentation is not visible.
Yes.
Now it is visible.
Yes, sir. Yes, sir. It is fine now.
Okay. Okay. Thank you. Okay. So once again, very good afternoon to all of you. Today, we will discuss about the structural analysis subject in detail. The very first topic of structural analysis, that is, we can say, determinate or indeterminate structures. What is statically determinate and indeterminate structures? So first of all, in introduction, we can say it is the application of solid mechanics. And what is mean by this structural analysis first? Now, if we consider a particular structure, in that particular structure, we have some number of forces, some number of known forces, some number of unknown forces. Known forces, the value of known forces we know, but the values of unknown forces we don't know. These unknown forces are in the form of, we can say, support reactions. Okay, we can say apart from the support reaction, we can say shear force, bending moment, axial forces. All these values or all these forces are all these forces are unknown forces. So a method in which we can calculate or we can determine these unknown forces with the use of known forces, that is termed as analysis. So particularly the structural analysis is what? The structural analysis is the determination of these unknown forces in the form of shear force, bending moment, axial forces, support reactions. Okay, so these unknown forces we have to find with the help of known forces for the given structure. It is that termed as structural analysis for a particular building. So our topic is statical determinate and indeterminate structures. Okay. Now, so statically determinate, first of all, we will discuss about statically determinate structure. What do you understand by statically determinate structure? It is that structure in which the number of unknown forces is calculated by using the equilibrium equations. Okay. So for different types of structures or for different types of different category of buildings or structures, we have different types of different numbers of equilibrium equations. For example, if we consider equilibrium equation for 2D structures and for 3D structure, if we consider 2D structure, means it is a planar structure, it is lie in one single plane, all members and all the forces lie in a single plane only. Okay, so in that system we have three number of equilibrium equations. Okay, so for a particular planar structure, if any structure is analyzed successfully with the help of these equilibrium equations only, then we can say that will be the determinate structure. Okay, similarly, if we think about 3D structure, so 3D structure is nothing but the space structure. Okay, all three dimensions are visible or all three dimensions are available to analyze. Okay, forces are coming from all the three dimensional, or we can say three dimensional forces are there. Okay, so in that case these forces are in 3D. So we have these six numbers of equilibrium equation, that is summation fx, summation fy, summation fz equal to 0, as well as summation fx, mx, my and mz will be equal to 0. And in 2D, there will be only three: summation fx, summation fy, and summation of moment equal to 0. These are the particular basic equilibrium equation for 2D and 3D structure. Okay. Now, in this presentation, I have basically covered more or less number of we can say details or number of numerical problem on 2D structure. Okay. So as it is our very first class, so in this lecture we will discuss about the analysis of 2D structures. Okay. So secondly, now this was the statically determinate structure, that structure that can be analyzed by using that equilibrium equations only. Okay. Now, statically indeterminate structure. Now, if any structure we have, that in that structure, if we can't calculate the number of unknown forces by using only equilibrium equations, then that structure is termed as indeterminate structure. Okay. So for that particular structure, we need a number of additional equations apart from these equilibrium equations. Now these additional equations termed as compatibility equations, compatible equation or compatibility equations. Now, what is this compatible equations, or what is that? What is the meaning of this? We will study further in the coming slides. So, for this, now statically indeterminate structure. So, when we think about statically indeterminate structure, there will be some degree. Degree in what? Means in what degree it is indeterminate. Okay. So, degree is nothing but the number. Means it will suggest that the what number we number that can be found out, or for what number of forces we can't found out by using these additional equations or equilibrium equations. So degree of static indeterminacy, it is generally denoted by d to the suffix small r or capital S, we can say. Then there will be two categories in static indeterminacy, that is external indeterminacy as well as internal indeterminacy. Okay. Now total indeterminacy will be summation of this external indeterminacy plus internal indeterminacy. Now this DAC and DSI. Now external indeterminacy, it's denoted by D to the suffix SE, and internal indeterminacy, it is denoted by D to the suffix SI. Okay. Now this DSE what and DSI is what? Now there are two terms, and there are these two terms comprises of total indeterminacy in that structure. Okay. So degree of external indeterminacy, simple. When any structure is considered to be in between unknown forces and known forces, means it is application of known forces on the unknown forces, that in the relation between these known forces and unknown forces, known forces and unknown forces, it is termed as external indeterminacy. Or what is the behavior, or simple we can say it is a behavior of a structure or a behavior of an object due to the application of known forces as well as unknown forces. Means all it's dependent upon the forces, whatever it is known forces or unknown forces, so totally it is dependent on forces. Whereas in internal indeterminacy, there will be a relation between the members. Means one member is subjected to some kind of force. So what will be the effect of one member to the another member? That will be the internal indeterminacy, or internal we can say relation. So external indeterminacy is nothing but the external relation that will be totally dependent on known and unknown forces, whereas internal indeterminacy is totally dependent on the number of members. So number of members in the sense, see in what regard one member is dependent or one member in relation with other. Okay. So this is the external indeterminacy and internal indeterminacy. So summation of these two factors will be the total indeterminacy for that structure. Okay. Now for plane structure, so external indeterminacy is calculated by using this formula. So number of support reaction minus equations of static equilibrium. Okay. So for plane structure, DAC can be calculated by using R minus 3, and for space structure, DAC can be calculated by using R minus 6. Okay. So now this, what is R? So capital R is the number of support reaction. So capital R, this capital R is the number of support reaction, And three is the equation of static equilibrium. We already seen in the previous slide. So for plane structure, for plane 2D structure, we have a number of equilibrium equations as 3. And for space structure, we have the number of equilibrium equations as 6. So simply, so reactions. So this for plane structure, so DAC can be calculated by using so R minus 3, so support reaction minus 3, and for space structure it is R minus 6. Okay. Now again, this is written in say words, so it is a shortcut of this. So DS is equal to DSI plus DSC. Now DSI, so internal indeterminacy can be found out by using DS, so total minus DSC. If we do, so we can get this DSI. Okay. Now then, now we have this equations of equilibrium condition we have seen. Now here for plane structure and for space structure, we have this capital value R, capital value of R. Now we will see this capital value R. What is this value R? So support reactions. So support reaction, there are basically 3 support reaction. I assume that you all aware of these 3 support reactions. So these 3 support reactions are fixed support, so hinge support and roller support. Okay. So for fixed support, there will be 3 reactions. For hinge support, there will be 2 reactions, and for roller support, there will be 1 reaction only. Okay. Now this reaction comes from. I assume that you know these support reactions as well as this reaction component from where it is come. But for the timing, I am discussing in short. It is what is the meaning of this Rx, Ry, Mz for the particular support. Okay. Now see fixed support means that if this fixed support means this is the particular wall and this is a particular beam and it is fixedly joined with each other. Okay. So there will not be any movement. There will not be any movement. Means this beam can't be moved in the vertical direction. This beam can't be moved in a horizontal direction, and this beam can't rotate in clockwise or anti-clockwise direction. Okay. When this wall is not there, only beam is present. And if I apply a horizontal load from right to left. Okay. So in that case, what will happen? So this beam will try to shift to the left because this wall will absent. Okay. Now if this, in the absence of this wall, if I apply the vertical downward force on this beam will swing downward direction. And if we try to this beam, I try to rotate this beam in clockwise or anti-clockwise direction, it will be possible. Okay. So, but in the presence of this fixed wall, what this fixed wall will do? This fixed wall will try to stop, or we can say this fixed wall will try to stop this beam action. Okay, after application of load, we can say. So if this fixed wall is there, and if fixed wall is there with this beam, and if I apply say horizontal force, vertical force, or rotation, so in that case this beam will try to impose a opposite force, we can say opposite force on this beam. Okay, this opposite force are nothing but this reaction. Means reaction is given by this fixed support or fixed wall to the beam is nothing but the reactions. So in this fixed wall provides the reaction in the horizontal direction, reaction in the vertical direction, as well as no movement is possible. Okay, no movement possible in the sense no rotation is possible either in clockwise direction or in anti-clockwise direction. So therefore there are 3 reactions, that is Rx, Ry, and Mz. Okay. Similarly for the hinge support क्या करता है? Hinge support holds our beam in horizontal and vertical direction. Okay, means what? If I apply horizontal force on the beam after application of this hinge support, this beam will not able to move in horizontal direction. Okay, if I apply the load on a beam in a vertical direction after application of this hinge support, the beam will not able to move in a vertical direction. But if I apply a rotation either in clockwise or in anti-clockwise direction, the beam will able to rotate in clockwise or anti-clockwise direction. So hinge support only provides the reactions in x and y direction only. Rotation is possible. Okay. Similarly, if I consider roller support, so roller support provides only the one reaction, means a base reaction. After this reaction, if I have provided here the vertical reaction. The vertical reaction means that this whole assembly, means this support as well as beam, cannot settle down. Okay. If this roller reaction is in the phase of vertical, so in that case, your beam cannot move in the horizontal direction. Now here the beam cannot move in the vertical direction. Okay. If I apply this roller support on vertical plane, so that in that case your beam cannot move in a horizontal direction. So only one platform is provided, and this is a roller. So this is a roller, means that on this roller this beam can move. On this roller this beam can move, as well as on this roller the beam can rotate in clockwise or anti-clockwise direction. So only one reaction. So it is a universal. So for fixed support it is a three reactions. For hinge support it is a two reactions, and for roller support it is a one reaction. So it is a, for plane structures it is three numbers. For fixed, for hinge it is two, and for roller it is one. Similarly, for space structures, it is, for fixed support it is six numbers. Okay. For hinge support it is three, and for it is roller support it is only one. Okay. So then, so now, sorry, any question? Now, now these are the live example of this fixed support, hinge support, and roller support. Now, basically, in practice, we can say this kind of picture shows the fixed support. This is the hinge support. In that, say this is the floor. We can say this is the wall. Means that this whole assembly can't move in the downward direction or in the vertical direction upwards, or whole assembly can't move beyond this wall, or uh, apart from this wall, means near to this man, or apart from this man we can't move. Okay. So only this beam can rotate here through this point, through this hinge. This beam can rotate. Only rotation is possible. Okay. Here it is, this vertical wall and this beam is fixed with this number of rivets, we can say. So in this, no vertical movement, no horizontal movement, no rotation is possible. So it is a kind of fixed support. It is a kind of hinge support. And this is a roller support. We can say this is the platform, this is the flooring. We can say this, beyond this flooring it can't move. Okay. This platform can't move in the upward direction, as this platform is coming. Okay. So in between the structure, or we can say beam, and this platform, there is a roller. So the movement of beam with respect to platform in the horizontal direction is possible only. So this is a live example of roller support. Okay. Then, so degree of static indeterminacy for frame structure, we can say. So there are two methods to calculate the static indeterminacy for frame structure. So uh, method one we will discuss here, and method two will be discussed after some slides. Okay. So for plane frame, so total degree of static indeterminacy is calculated by using 3c minus r dash. Okay. Now, these terms r and r dash, several time in this presentation, several time you will find the notation capital R and capital R dash. So don't confuse in that capital R and capital R dash are similar. Okay, don't confuse that, or don't assume that capital R and capital R dash are similar, or don't assume that capital R dash sir have done some mistake and capital R and capital R dash are similar. Okay. So capital R and capital R dash are different. Okay. I again repeat, capital R and capital R dash are different. By the time when we solve the numerical, I will explain what is capital R and capital R dash. Okay. Uh, uh, in the previous slide, I have already displayed that capital R is the number of unknown reactions, and capital R dash, it is written as number of restraint to make all joints rigid. Okay. Now this formula here, it is given as formula 3c minus R dash and 6c minus R dash. Okay. Now for the timing, we can say, or you can judge that for a particular frame, we can say simply for particular frame, we have to calculate ds, that is total degree of static indeterminacy. So we have this formula. Okay. Many times student do that, रट लेते हैं फॉर्मूला 3c माइनस आर डैश 6c माइनस आर डैश रट लेते हैं कि ds निकलना है तो मुझे ये फॉर्मूला यूज करना है. ओके. फॉर द कैलकुलेशन ऑफ ds I have to use this formula. For the calculation of space frame I have to use this formula. But from where this 3 comes and from where this 6 comes. Okay. So nobody in that picture that from where this 3 has come and from where this 6 has come. Okay. So further I will tell, but for the timing we will see the notations. Okay. So for plane frame ds is equal to this formula, and for space frame ds is equal to this formula, where c is the number of cuts to make structure determinate. Okay. Capital C is the number of cuts to make structure determinate, and R dash is the number of restraint to make all joints rigid. Okay. Now then second method, we can say second procedure, we can say. First procedure is that we have a simple formula to calculate ds. Okay. Now for the application of that formula, we have to convert our structure in a particular way that we can analyze the structure. Okay. By default frame hai, beam hai, whatever is the structure, or stress hai, whatever it is, it is given as an example. Okay. First of all, we have the task that we have to convert that in the determinate form so that we can analyze that structure simply. Okay. So what is the procedure? So what is the procedure is simple. So determinate, we have to make a tree like structure. You know, tree, a simple root is there and number of branches are there. Okay. So tree have, so one root is there and number of branches are there. Okay. So again, so this is a procedure, simple procedure. Whatever frame, now we are discussing here about frames. So first of all we will discuss about the frame, then beam, then truss. Okay. So for frame we have this formula again. Okay. 3c minus r dash, we are discussing here about 2d first. So we have to use this formula 3c minus r dash. Okay. C is again this number of cuts and r dash is number of restraint provided. Okay. Okay. Now, and we have to convert our structure like tree, one root and number of branches. Okay. Then now this restraint requirement means what is the value of r dash? This r dash requirement, number of restraint required to make a joint rigid equal to number of support reaction for a fixed support minus the number of actual support reactions. Okay. So r dash will be equal to r of fixed support minus capital R of actual support. Okay. Means, for example, we can say, see, R of fixed support will be what? Capital R will be 3 in number. Okay. What was that? Summation fx, summation fy, and moment. Okay. These 3 reactions are for fixed support. Okay. We have seen these 3 reactions are for fixed support, Rx, Ry, and Mz. So these 3 numbers are there. So these 3 numbers are this fixed support are 3 numbers. And if actual support is hinge support, suppose. So this 3 and actual support is hinge. So for hinge support is 2 reactions. So R dash will be what? So R dash will be 3 minus 2 will be 1. Okay, simple. So R dash, it is dependent on R. So what is the number of reactions for a particular support? That on that this R dash is dependent, totally dependent on that reactions. So R dash is equal to that. We can say, for example, if fixed support and it is a hinge support, suppose, so 3 minus 2 will be 1. So R dash value will be 1. So additional restraint required to make it fixed will be 1. So one reaction we have to provide to make it fixed. If the fixed support is having 3 reaction, if actual support means in the problem we have only roller support. So roller support only have 1 reaction. Again, so roller support again we have this only 1 reaction. So for roller support we have If I put this for roller support, R value for roller support, so R dash will be 2. So two additional reactions we have to provide to make it rigid joint. Okay, simple. It is the meaning of this R dash. Okay, don't confuse with R dash and R again. Okay, now if any member have internal hinge, if any member have internal hinge, so in plane frame this is the formula, and in space frame this is the formula. Okay, now in plane frame m minus 1, where m is the number of members, and again in space frame it is multiplied by only 3, so it is nothing but it is multiplied by 1 into m minus 1. It is means only one plane. It is 3 stands for 3 plane. Okay, 3D structure is there, so 3 stands for this. Basically formula is same, so it is don't रट्टा मत मारो. It is समझ के लो कि यहाँ पर 3 क्यों आ रहा है और यहाँ पर m minus 1 क्यों आ रहा है. Okay, so number of restraining moments are required. So normally restraining moments directly इसलिए बोला गया है because when we consider hinge support, there will be two reactions only. Okay, vertical reaction or horizontal reaction. There will be movement possible, rotation is possible, so moment is possible. Moment is not possible, rotation is possible. So that's why only one reaction is possible, that is moment. That's why whenever there is an internal hinge, there will be restraining moment only. Okay, so for the internal hinge, there will be restraining moment. So m minus 1 again, if a joint comprises of 4 members, so there will be R dash will be over 4 minus 1 will be 3. If a single beam is there and one internal hinge is there, so one internal hinge will with single beam will divide our beam into two part. So value of m will be 2 and 2 minus 1 will be 1. Okay, so one reaction we have to provide to make it fixed. Okay, so space frame, for a space frame again formula is same, but this 3 stands for 3-dimensional. Okay, similarly these were the some conditions. Also these were the these are the also some conditions. If this is a beam, this is a beam, this is a beam, and this is a roller support. Okay, now if I apply a load on this, or if I apply a force on this assembly, so we can say this beam will move, means this roller can move in a horizontal direction. Okay, but if you consider this is the platform and this is the platform, so in that case our beam can't move in the vertical direction. But whereas we can say about this point the beam can rotate. The beam can rotate. This can displace anywhere. This joint can displace anywhere, but this joint can rotate either clockwise or anti-clockwise direction. So there will be a number of restraint required is what. So horizontal movement is possible. So that means we have to restrict that horizontal movement, as well as this rotation is possible, means we have to restrict that rotation. Okay, so therefore number of restraint required are 2, that is horizontal reaction as well as movement. Okay, so similarly for second it is very simple. if एक बार समझ गए तो पूरा समझ में आ जाएगा. ठीक है, it is simple. Second, this is a beam, this is a beam, this is a we can say this is the upper platform, this is the lower platform, we can say, and these are the number of rollers. From by seeing this assembly we can predict that these platform or beams we can move in the horizontal direction only. No vertical displacement is possible, no rotation is possible. So we have to restrict only horizontal movement, so only one reaction is required. So R dash value will be only 1. So that will be your horizontal reaction. Okay. Similarly, if these rollers are fixed in the vertical direction, okay, so again these are in the horizontal direction and these are in the vertical direction. Again the similar case, no rotation is possible, only vertical movement is possible, no horizontal displacement is possible. So only one reaction is required. So R dash value will be only 1. So RV value will be 1. Okay. Now, sir, say example. Simple example. So it is a double story, a single bay portal frame is given, and we have to calculate, say, total degree of indeterminacy, say internal degree of indeterminacy as well as external. Okay. So the first figure shows the example problem. This first figure shows the example problem where see first support is hinge support. Okay, second support, bottom support is roller support, and in the first member there will be there is an internal hinge, and in the last member there is an internal hinge. Okay, if I consider this is the member 1, 2, 3, 4, 5, and the 6. So in member 1 there is an internal hinge, and in member 5 there is an internal hinge. Okay, now according to our, this is a plane frame problem, 2D plane frame problem. We have the condition what? So we have to make it determinate like tree like structure. So the that have only one root and number of open branches. Okay, so for that, what we'll do, we will cut this frame into center line bolo ya agal bagal mein bolo. So randomly we will cut this whole frame into this single line. Okay, after cutting, what will be what will have? See, if I cut, so this will be my root, you can say this is my hinge support. Okay, so this will be my hinge support, this is a, we can say this is a root. Okay, and if I cut this, if I cut here, if I cut this whole frame from here, so we can say after cutting this two frame will be move apart. So will, this will be our first part, and this will be our, so the this will be our roller support, and this will be our this. Okay, so there is a internal hinge here, and there is a internal hinge here. Okay, so after making, after cutting our building frame, so it is a form of a tree. See, this is a root, we can say a hinge support is a root, and this is a one member is there, one we can say one member from root, we can say, and these are the number of branches coming from this one member, one parent member, we can say. Okay, similarly for these. Okay, so for these, for making of these structure determinate, the number of cuts required are two. So first cut is there this, and second cut is this. So number of cut required is two. So number of cut required are two. Okay, now 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 h1, we have h1 and h2, that is internal hinge. Okay, for this member and this member. Again, if we have internal hinge, so for internal hinge we have this formula, m minus 1. So number of restraining moments are required internal hinge for internal hinge. So for at h1 m minus 1 formula for 2D plane frame. So this single member will be divided by using this internal hinge into two parts. So 2 minus 1 will be 1. Okay, and for h2, for similarly for h2, again this internal hinge will divide this whole beam or member into two parts. So again m minus 1 will be 2 minus 1 will be 1. So r dash value at h1 will be 1, and r dash value at h2 will be 1. Okay, so we are calculating h sorry, r dash. Okay, so first of all we have calculated capital C, that is number of cuts. So number of cuts required are 2. Okay, so number of 2, I reflected total here. Below bottom is, it is a total. Okay, so whole calculation is here in this table, whole calculation in the first row itself. Okay, now at a, r dash is required is 1. Now how is r dash is required is 1 at a? Okay, now see, r dash at a, we can say this is the r dash, this is the r dash, we can say this is the hinge support we have. Okay, now in the previous slide we have seen r dash is equal to r fixed support minus r actual support. Okay, so we have to make it fixed. We what is our aim? To make it fixed. If I have to make it fixed, so number of additional reactions are needed. What number of additional reactions are needed? So by using this formula, we have r, it is 3, and this is actual support is hinge. So for actual support hinge, it is now addition actual reactions are 2. So 3 minus 2 will be, so 1. So r dash will be 1. So similarly for at a, r dash will be 1. Okay, similarly for this roller support, for roller support again, or roller support again, r fixed minus r actual. So 3 minus, again 3 minus, for roller support there is a only one reaction, parent reaction r. So 1, so therefore it is r dash value will be 2. So At B, R dash value will be 2. Okay. Now simply summation of this. So 1 plus 1 plus 1 plus 2. So total is 5. Okay. So 3 plus 2, it is 5. Okay. So value of C is there. Value of R dash is there. Simply we have to put the values in this formula 3C minus R dash, and we will get this number of degree of indeterminacy. So this is the 1 degree of indeterminacy in this structure. Okay. Then simply DAC, if we calculate DAC, so capital R minus 3, so number of known reactions for we can say rigid, these all supports or all these joints we can say in a frame, in a plane frame, we considered as rigid joint. And for rigid joint, we considered these three reactions, that is rigid joint can't move in vertical direction, rigid joint can't move in the horizontal direction, as well as no rotation is possible. Okay, so that's why it is 3 is there. So 3, so 3 number of reactions minus 3. So 3 are the nothing but the number of equilibrium equations. So DAC is equal to R minus 3. So 3 minus 3 is 0. Means externally it is determinate. Externally it is no problem. Okay. Internally, if we say, so DS minus DAC, so again 1 minus 0 will be 1. Means internally it is indeterminate, or we can say internally it is unstable, we can say. Okay, now what is the reason behind this? It is internally unstable. Okay, now we have seen total, though it is externally stable or externally determinate, but internally it is indeterminate. So that's why it is total number reflected here. So total number is reflected as 1. So it is the given frame is indeterminate to degree 1. Okay, either in externally or in internally. So internally here it is indeterminate. Okay, or we can say internally it is not stable. Okay, so what is the reason behind this stability? So further we will discuss in the further slides what is the what kind of stability is there and what kind of parameters are there. Okay, now second problem. For second problem again, so second problem, these frame is given. So by default here support reactions are given as fixed support. Okay, again we have to make the tree like structure as per the procedure. So I have cut this whole frame into number of cuts, we can say. So for first cut, this is second cut, this is third cut, the fourth and fifth. So number of cuts are required are 5. So number of cuts required are 5. Okay. Now these all are the fixed supports. So no additional reactions are needed to make it fixed. It is already fixed. Okay. And only the R dash value will come only here. So internal hinge is provided. So internal hinge is connected with 4 number of member. In the previous problem, internal hinge was connected with only 2 member. Okay, so there were 2 minus 1. Here internal hinge is connected with 4 member. So 1, 2, 3 and 4. So these 4 members, that's why so R dash is m minus 1. So R dash will be 4 minus 1 will be 3. Okay, so R dash will be 3, C will be 5. Again directly DS is equal to 3, 3C minus R dash. So we have 12. Okay, so here for this particular structure the degree of indeterminacy is 12. Okay, then for space frame, sorry, for plane frame method 2 is there. Okay, so for again it is rigid jointed structure. If I consider about plane frame, so it is rigid jointed structures. So in method 2, it is in a plane frame, each member carries 3 forces. What are these 3 forces? So this is shear force, bending moment and axial force. So these 3 forces in plane frame. Okay, so hence total unknown forces are there. Total unknown forces are, we can say, m minus r, sorry, m plus r. Total unknown forces are m plus r. Again 3 has come here. So what is this 3 denoted? What is the meaning of this 3? So again, this shear force, bending moment and axial force, these are 3 in number. Okay, and we can say, we are saying that each member carries 3 forces. So that's why this m is multiplied into 3. So that is 3m plus r. Okay, so basic equation is m plus r, but here in for the case of plane frame rigid jointed structure, each member carries 3 forces, that is shear force, bending moment and axial force. That is 3 forces. So that's why number of unknown forces are for a particular member or for a particular structure 3m plus r. Okay, where m is number of members, r is support reactions. Okay, then at each joint number of equilibrium equation is 3, we know as well. As a rigid jointed structure, number of equilibrium equations are 3. Summation of x equal to 0, summation of y equal to 0, summation of moment equal to 0. Okay, then so total number of equations of equilibrium, that is 3j. J stands for joint. So for a particular joint, there will be 3 equations of equilibrium. Okay. Hence, total static indeterminacy for a particular plane frame is 3m plus r minus 3j. Means we can say again it is a blend of known forces as well as unknown forces. Okay. Okay. So this relation is 3m plus r minus 3j. So these 3j and 3m plus r. This 3m plus r we don't know. Support reactions we don't know. We have the loading value. Okay. These 3 equilibrium equations we have no. Okay. Summation of x equal to 0, summation of y equal to 0, summation m equal to 0. These 3 equilibrium equations we know, but these member forces, but plus these reaction forces we don't know. We have to calculate that forces later on depending upon the number of loading is available. Okay, then similarly for this ds will be equal to 3m plus r minus 3j will be only for plane frame, means no internal hinge, nothing. Okay, simple plane frame is there. So in that case ds will be calculated by using this formula. Okay, now plane frame with internal hinge, so simply this fraction is same to previous one, only the minus again summation of m minus 1 is added, means subtracted from this whole term. Okay, similarly for space frame, again this again six number of unknown forces, so member into multiplication of this 6 plus r minus 6j. Similarly for this space frame with internal hinges, again this 6m plus r minus 6j and summation of m minus 1. But these 3 again I have declared already or discussed already that 3, so these 3 are nothing but the 3-dimensional coefficient we can say. So it is 3 is there. Okay. Else this formula is same, but only here is 3, here is 6. Okay. So for beams and total degree of static indeterminacy is calculated by using support removed minus constraint added. Now see, for frame we have used this term r and r dash. So we have r is this we can say support reactions, and r dash is restraint added we can say. And here it is new term is there, so constraint, that is capital C again we can say. Okay, so constraint, this constraint is nothing but this r dash. Okay, so for frame we have used this notation is r dash, but for beam it is used as constraint. This constraint are nothing but the restraint added for the particular structure or particular beam. Okay, now example, a beam example. So beam example is there. So make for, here is also a simple procedure that our beam, this is a given beam, and we have to convert this beam into cantilever like structure. We have to convert this beam into a cantilever like structure. Okay, now if for a particular beam, if I have to convert this beam into a cantilever like structure, what will do? This A support is already fixed. It is no problem. Means cantilever beam is what it is seen like this. Means this first support is fixed, and here it is free. It is totally free. Okay, this is free. This is fixed, and on one end is fixed, and another end is totally free. Okay. Now here it is not the case. Here support A is fixed. It is okay. But here it is another support, that is B, another support, that is C. Okay, and with that one additional hinge is also provided. Okay, so our first target to remove all these 3 parameter, that is internal hinge we have to remove, this support we have to remove, and this support we have to remove. Okay, so now support remove means what? Support removed is what means what? So support remove means what? Number of reactions related to that support that removed. Number of reactions related to that support is removed. Okay, not r dash again. Not confused with r dash again. Okay, we have to remove r. we have to remove r, we don't have to remove r dash. Okay, so for a particular this structure, make for making cantilever beam, so for a support b, we have only one reaction. So this r value is only one. For this is roller, b is roller support, at c it is roller support, so reaction is one. So this is again r, this is again r. Okay, so remove this both the supports. Remove this support at b and remove this support at c means what? So keeping A is fixed, so keeping A at fixed as it is here already provided that, and that's why it is as it is written. Okay, then so number of support removed 1 plus 1. So number of reactions removed actually. Number of supports they are removed. If there are hinge support, so there will be 2 plus 2 will be 4. If these two will where will be the hinge supports, then total reaction or total support removed will be here it will be 4. Okay, the next problem, there were the hinge support, we will discuss further. So here it is a ruler support, so for ruler support reaction is only 1. So for removing these supports, so support removed is 1 plus 1 is 2. Then constant added. Constant added is nothing but the restraining moment at D, means it is internal hinge, and we have to remove that internal hinge. Again, this type of problem we have seen. Similar formula we have to use, that is m minus 1 we have to use again, and this hinge making is A to B, AB into 2 halves AD and DB. So again, m minus 1 will be 2 minus 1 will be 1. So again, C constant added, that is capital C we can say. Okay, so constant added capital C will be nothing but r dash will be equal to 1. Okay, so hence ds will be equal to what? Support removed minus constant added. So 2 minus this 2, 1 plus 1, it is 2 minus 1, it is 1. Okay, so beam is indeterminate to degree 1. Simple. So it is a simple. Okay, next one. So this problem seems to be very bigger. Number of supports are there. Okay, two number of hinges are there. Okay, total number of 4 supports are there provided. But this beam, a long beam, it is a determinate beam. How it is determinate beam? So we will see. Again, after the procedure, we will have to make this beam is cantilever beam. So for making cantilever beam, what we have to do? Make this hinge support as fixed support. A has hinge support. First of all, make it fixed support and remove support B, E, and F. Make it as fixed support, hinge support at A, make it as fixed support and remove support B, E, and F. Okay, so make it A as fixed. Okay, hence number of support removed. So again here it is one reaction. Again roller support, it is one reaction. Again hinge support, there will be a 2 reactions we can say. Okay, so again one at B, one at E, and 2 at F. So total number of 4 at is total number 4. So number of support reactions removed at 4. Okay, so then constant added at C. So first internal hinge, second internal hinge. Okay. So due to this first internal hinge, your member one, your BE is it is divided into this part and this part. Okay. So at C will be m minus 1, again 2 minus 1 will be 1, and similarly at D, m minus 1, 2 minus 1 will be 1. Okay. So constant added at A, again constant added at A, again the previous formula, actual R fixed support minus R actual. So R fixed support is 3 and R actual is only 1, so 2. So that's why constant added is 2. Okay. Again, I am repeating. Again, I have used this formula here. What was the formula? This formula is this R fixed support minus R actual support. Okay. So here R fixed support is 3. So R fixed support is 3. Sorry. R fixed support is 3 and R actual support is roller support. It is 1. So one reaction for roller support. So this 3 minus 1 is 2. So that's why constant added is 2 at D. So summation of these, all these, so 1 plus 1 plus 2, so total 4. So total constant added is 4. So hence ds is equal to support remove are 4 in number and constant added are 4 in number. So 4 minus 4 is 0. So that's why it is determinate beam. Okay. Similarly, another beam, it is again simple, again similar. Make it make it cantilever beam. So this beam is seen like this. So we have to make this beam like this. So this we have to make this support A as fixed support, but already A has fixed support. But we have to remove this internal hinge, this roller support, as well as this fixed support at D. Okay, so remove support D. So hence number of support removed at D. So 3, it is fixed. So we know our capital R value for fixed support, it is 3, Fx, Fy, and M. Okay, so these there are 3 reactions. So we have removed 3. Constant added to B, again M minus 1, so 2 minus 1 will be 1, so this will be this. Then constant added at C will be roller support. Again, we have seen here, we have the case C. Look, carefully see in the box, see the case. This is the case with us, and we have the relation. Again, already have discussed. So this is that relation, we can say, and number of resistance required are 2. So RH and M. Okay, so RH and M is required. So that's why number of support remove. Sorry. So here, so number of constant added at C is 2. That is 2 RH and M. Okay. So it is previously discussed. Hence, the total constant added is 1 plus 2, it is 3. And hence, DS total degree of static indeterminacy will be support remove, means support reaction removed, and constant added means R minus, we can say R dash. So this will be 3 minus 3. So this 3, this is 3, this is 3. So it is 0. Again, it is determinate beam. Okay, simple. Okay, then another example, again, make it cantilever. Okay, so again, it is a determinate beam. Now here again, I am not discussing about B, F, G, C. Okay, I am discussing only this link DE. Okay, again, we have to make this beam as a cantilever beam. So make it as like this, and this will be your joint A. And at joint A, this is a hinge support. So 3 minus 2 will be 1. So resistance added at A will be 1. So constant added at B, it is hinge. M minus 2 minus 1, it is 1. At D again. So at D and E, these are nothing but the internal hinges connected with 2 members. This internal hinge D is connected with this member and this member. Okay. Similarly, internal hinge at E, it is connected with this member and this member. So again, the member are 2. Here the members are like this. It is internal hinge and member in the horizontal plane, but here it is what? So member is like this and internal hinge is this. So again, similar to this beam, so number of members connected are 2. So M minus 1, 2 minus 1 will be only 1. So, okay, so D will be 1, and similarly E will be again 1. Hence total constant added will be 4. So 1 plus 1 plus 1 plus this at A will be 1, and number of support reaction removed are 4. So 1 at C, roller support, 1 at F, roller support, 2 at G, hinge support. So 4 is this, and 4 is constant added. So 4 minus 4 is 0. So again, it is a determinate B. Okay, simple. Then we will discuss about shortly stability of structure. See, again, there will be 2 types of stability: external and internal. Okay, so body sufficiently constrained by external reactions or forces. In that case, we can say the body is externally stable. But when movement of one part of a structure with another part or with respect to other part, then in that case we can say this structure is not stable. If there is no movement, then in that case means there is no movement of one part of a structure with the help of with respect to other. In that case, we will see, we can say that this structure is internally stable. But if there is a relative movement, then we can say the structure is internally unstable. Okay, so these are nothing but externally stable. We can say these are the rigid bodies. Okay, that are externally stable means that after application of force, nothing will do. No significant changes in the geometry or no significant changes in the displacement is there. Okay, so 3 planar reactions should not be see. These two are the conditions. Means what? If these 3 reactions are concurrent, 3 reaction for a particular meeting at a particular point, so that structure will not stable. Again, similarly, if 3 parallel forces is there, so in that case also this for the particular body is not externally stable. So examples are, so externally instability ki example dekh lo. So if these are the parallel forces, mean this roller support, this roller support, this roller support is there. Three roller supports are there, three vertical reactions are there, but no horizontal reactions is there. Means what? When I apply this force on a particular beam, this beam will free to move here, here and there. There is no restriction on horizontal movement. Means it is not, if it is not stable at a place, means it is a unstable. So externally means due to application of force, it is externally unstable. Similarly, for concurrent forces, if I apply this line of action of these two reactions is concurrent meeting at this point, and if I apply the force from this, so it is free to move in this, means it can move in the in these two directions. In that fashion, it can move. So again, it is not stable. Okay. Concurrent forces, this is the example of concurrent forces. Again, this is the example of concurrent forces. So we can see this is a, so in this horizontal reaction, we can say this is a counterbalance each other, but this is the roller support. And if I apply this vertical force or vertical reaction, or in here any vertical reaction or vertical force here, so structure can move in the vertical direction. Okay, so this is again example of instability. Then internal instability. So this is the first example is three hinge formation or three hinge mechanism. We will not discussing in detail about three hinge mechanism because it is a very first lecture, and in the first lecture it is not sure to discuss about three hinge mechanism, but only take about three hinge mechanism is that it is a failure condition. So if these three hinges are in a plane or in a line, we can say, so there will be a three hinge mechanism formation, and this will be will cause to a failure. Okay. Now this is unstable because see this joint is at a lower position, this joint is upper position, but there is no bracing or there is no in between support. So there will be a relative motion of this joint with respect to this. Okay. So there will be a relative motion of one joint to another, so it is internally unstable. If I apply this bracing here, so it is after applying this bracing, it will be provided giving the strength to this joint, we can say. So in that case, this structure we can consider as a stable. So internally we can consider as a stable. So static indeterminacy for trusses. Okay. So again, for plane frame, there will be number of equilibrium equations will be three. Here it will be two because it is a pin jointed, and pin jointed are nothing but the hinge like hinge support, and only two reactions are there: summation fx and summation fy. Okay. So for plane frame, there is a fx and fy equal to 0. For plane frame, plane truss, it is 2. For space truss, it is 3. That is summation of x, fy, and fz equal to 0. So number of unknowns are there. Member forces is there. Here shear force bending moment is not come. Here only the axial forces as well as the reactions. So support reactions. So total number of unknowns are m plus r. Okay. So with respect to one member, only one unknown force is there, that is axial force, that due to which here is coefficient is only 1. So that's why it is written as m plus r. So again, m is number of member and r is support reaction. Okay. Now there are several conditions, that is m plus r minus 2j equal to, if 0, then it is termed as statically determinate. If it is greater than 0, it is indeterminate, and if it is less than 0, so that particular truss is unstable. Okay. Then example. So example, these trusses provided to us. So this is a problem with three roller supports. So we have number of members. So we will count the number of member 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have 9 members. We have support reactions, again roller support. So one reactions is there. So 3 reactions are there. Number of joints are 6. So we will 1, 2, 3, 4, 5, and 6. So 6 joints are there. So again, application of this equation, m plus r minus 2j. So we will get a 0. So statically determinate, but externally unstable. Again, this 3 roller support, if I apply this horizontal force on this truss is free to move in a horizontal direction. So that's why it is statically determinate, but externally unstable. Okay. Similarly, try for this again. If I count this number of members, it is 10. Number of support reactions are 2. Again, 2 roller supports to 2 reactions. Number of joints are 6 again. And after application of this equation, so we have 0. It is statically determinate but externally unstable. Again, 2 roller supports are there. If I apply this force is there, so it is free to move in a horizontal direction. So third example, so number of members are again 9. Support reactions are 3 because this is a hinge support. There will be 2 reactions, and this will be roller support. There is a 1 reaction. So number of reactions is 3. So number of joints are again 6. So after application of this, it is 0. It is statically determinate but internally unstable. Why internally unstable? See, these particular we can say members are connected with these bracings, but this is a open. So in this case, in that case, the internal instability may occur. Okay. Now this problem is provided for you. That is exercise. You can calculate by using this simple number of members you have to count, number of support joints, your number of nodes you have to count, and number of support reaction you have to count. After application of this equation, we can calculate the degree of indeterminacy for the particular truss. So this is the example problem, exercise problem for you. Okay. So internal and external and internal indeterminacy for plane truss. So these were the formulae. Internal indeterminacy is calculated by using this equation, and external again r minus 3. It is similar to plane frame. So again, if I added these two equations, so finally I will get this equation. So m plus r minus 2g. Okay. And here some conditions are there. If number of members are greater than this fraction 2j minus 3, so it is internally indeterminate and stable. If m is less than this fraction, the internally unstable. And if m is equal to this, so it is internally determinate and stable. So these conditions are important. In many cases or many many exam problem, these conditions are asked. These conditions are very much important. Okay. Then for space truss, it is given. So number of this is equation relation. Again, this here 3 coefficient is 3 is there, and here is 6 is there, because the number of unknown reactions we can say it is 6. Okay. So again, if after doing this calculation, we have this formula. Okay. So if ds is greater than 0, it is indeterminate. If ds is less than 0, it is unstable. And ds is equal to 0, it is determinate. But stability should be checked. Okay. ds 0 agar hai, to it is determinate, but like this condition, these both conditions, stability we have to check. Okay. So due to this roller support, this is unstable. Due to this roller support, it is unstable. So by seeing this stability by naked eyes, stability should be checked. Okay. Now kinematic indeterminacy. Again, it is another method, or we can say static indeterminacy means we are analyzing all the bodies at rest. We are calculating the indeterminacy, degree of indeterminacy at rest. But here in kinematic indeterminacy means we are taking the movement of a particular joint or movement of particular body in picture. Okay. So basically in the static indeterminacy, forces were the basic unknown, and here in stiffness method, displacements are the basic unknowns. We have first calculated displacement, and then we relate this displacement to the force, and by using that displacement for relationship, we can calculate the indeterminacy. Okay. So here again, the relation between load and displacement at a joint. Use of equilibrium equation to calculate joint displacements. Okay. In that case, we used that compatibility equations apart from this equilibrium equation. But here we will using equilibrium equation to calculate joint displacement. So number of unknown joint displacements called as degree of freedom or degree of kinematic indeterminacy. So dk is nothing but total possible degree of freedom minus available support reactions. Okay. So these are possible degree of freedom. Possible degree of freedom. It is not actual degrees of freedom. It is possible degrees of freedom. Means if I consider plane frame, rigid jointed, so there will be possibility that horizontal movement is possible, vertical movement is possible, rotation is possible, but not the case with that. We have these three reactions, that we have reaction in x direction, we have reaction in y direction, and we have moment. Okay, so possibility that that degree of freedom is a particular means in that direction the structure can move. Okay, but in practice or in practical situation it's not the case. Then space frame, for space frame it is 6 in numbers. Plane truss it is 2 in numbers, means this theta term is neglected, only this horizontal and vertical movement. And space truss again 3-dimensional, movement is there, no rotation. In case of trusses there will be no rotation value, only movement is, only displacement possible. Okay, so dk can be calculated by using 3j minus r minus m dash, 6j minus r minus m dash, and 2j minus r and 3j minus r for a space truss, where m dash is the number of inextensible member. Now inextensible member is what, so we will discuss about with the use of this example. Now see, if I consider this plane frame example, so this plane frame example, in plane frame example this joint is fixed, this is roller, this is hinge, but this is the case that we have this reaction at roller support. This is the case we have to we have reaction at vertical and we have reaction in horizontal, means this is fixed, this is fixed, this is fixed, this is fixed. Okay, so it is purely fixed, but it's not, in these two cases it is partially fixed. But if we think about the plane frame, so these joints are, we are considered these joints are rigid, means all the case these all the joints are rigid, means all the joints are fixed, we can say. And for fixed joints this member can't move apart from this joint, this member can't move at this level, below this level, this member can't move below this level. Similarly horizontal member can't move beyond this member, this horizontal member can't move beyond this member. Similarly for this, for this, for this, for this. Okay, so all these members are inextensible member. Okay, because all the members are connected with fixed joints. So number of inextensible members are m dash, so it is 10. So what, 1 2 3 4 5 6 7 8 9 and 10. So number of inextensible members are 10, so these are 10. So number of support reactions are 6. Okay, so support reaction here 3, here is 1, it is 2, so it is 2 plus 1 plus 3, it is 6. So support reactions are 6. Number of joints are 9, so 1 2 3 it is it is countable, so these are 9. So apply, hence dk is equal to 3j minus r minus m dash, so by using this, so it is 11. So 11, so degree of indeterminacy for a particular plane frame, so kinematic indeterminacy for a particular plane frame is 11. Okay, so it is again unbraced building frame, again it is we can say internally unstable. Okay, it is, we have considered this rigid joint, but we can see that it is internally unstable, so it is unbraced building frame. Okay, so force method of analysis. So purpose of choose statically indeterminate structure compared to statically determinate structure as follows. Okay, many situation in many situation indeterminate structure is preferable than the determinate structure, because indeterminate structure gives the smaller values of maximum stress as well as deflection as compared to determinate structure, as well as redistribution of load property. Redistribution of load property means that if I apply the load, if I apply the load for a particular structure, if a structure is fixed, all this structure is fixed. If I design this load for 20 kilonewton, suppose for example, if I design this frame for 20 kilonewton, okay, but due to some faulty design, means whatever material we have used for these members, horizontal, vertical member, whatever material used, if it is faulty, okay, but if it is faulty, again the case will be 20 kilo, it is designed for 20 kilonewton, but I have applied say 25 kilonewton. Okay, so in that case what will happen, this frame will fail. Okay, due to this faulty design, faulty workmanship, or whatever is the load. If I say this is a design for 20, but actually it is designed for 15, so that will be the also the case, means it is a faulty workmanship. Okay, faulty material. So in that case, the determinate structure will fail. But whereas in case of indeterminate structure, what will happen? So if I design for 20 kilonewton and if I apply for 20 kilonewton, so somewhere additional load will distribute somewhere due to that indeterminacy. Okay, so that's why indeterminate structure uses of indeterminate structure is preferably well than these determinate structures. Okay, so any statically indeterminate structure should satisfy these three equations. We also studied in the previous slides. In the static indeterminacy, we have seen compatibility equations. In the kinematic indeterminacy, we have seen it is a use of equilibrium equations. And so blend of these are in the both the method is nothing but the force displacement relations. Okay, so differences are, so force method is nothing but we can say force method is compatibility method or flexibility method we can say, whereas displacement method is stiffness method. Okay, basic unknowns are again forces, axial force, shear force, and bending moment. Whereas here displacements either in linear form or in the form of rotation. So it is a linear or in the form of rotation. Okay, so here use of compatibility equation with equilibrium equations, but here purely use of equilibrium equations only. So this method is suitable when ds is less than dk, and then this is suitable where dk is less than ds. It is the general condition. Okay. Now these are the examples of these force method, and these are the examples of this displacement method. So force method comprises of these methods, means these all the methods are dependent on or based on this force method. So this is the Classic-Connor's theorem, strain energy method, then unit load method, three moment theorem, column analogy, like that. Okay. Then displacement methods are slope deflection method, MDM, okay, stiffness matrix method, Keynes method. All these methods are dependent on this displacement displacement method. Okay, so these are the is. Then principle of superposition, principle of superposition is simple. In the first lectures of mechanics, we may have seen that principle of superposition in case of forces. Now, this same principle of superposition is applied in case of here is displacement. There it is discuss about the forces, means what is a summation of forces is equal to the effect generated by each force separately. Okay, so here is also same, but here we have considered displacement. So whole displacement of a body is nothing but the displacement generated by each number of forces separately. So it is given, and there are two basic conditions for that. So it worked between these two, between Hooke's law, means linear elastic responses, means strain is related directly proportional to stress. So in between these it is applicable, and small displacement theory means what, that assumption that after application of load no significance we can say geometrical change is not there. So basic whatever is the basic clauses or basic assumptions are there. On the basis of this basic assumption, if this theory is dependent. Okay, so that's for today. Thank you. Any questions for now? So we have discussed today about this. Uh, so we have discussed about this number of determinate indeterminate systems, as well as plane frame numerical trusses problem, as well as beam problems. Some problems are discussed, as well as we have seen the formulation for the kinematic indeterminacy, as well as we have seen the difference between the force method as well as the displacement method and application of these. Okay, so these were the content for today. Okay, thank you. Any questions are there? Please ask.
Thank you very much, sir. Thank you for sharing your vast knowledge with our students. Now I open this session for question answer. If you have any query, then please ask.
Any queries?